Good morning. I'm Christine Sa. Welcome to this news briefing from the 250th National Meeting and Exposition of the American Chemical Society in Boston. We're joined today by Dr. Stuart Licht from George Washington University. He's going to talk to us about a new approach to removing CO2 from the atmosphere, turning it into carbon nanofibers. Dr. Licht.
Thank you very much. One of the great threats facing our planet is climate change. Rather than attempt to survive the climate change consequences of flooding, wildfires, starvation, economic disruption, human death, and species extinction, we must mitigate the greenhouse gas, carbon dioxide. Sequestration attempts to bind carbon dioxide within other substances by blowing CO2 back into the ocean or bubbling it into the earth or other methods. But sequestration is fraught with uncertainty, high costs, and is unlikely to succeed. We report today that we have found a viable solution to mitigate climate change. Instead of sequestration, atmospheric carbon dioxide is directly transformed into stable, useful, compact, valuable carbon products. In the simple procedure, the carbon dioxide is converted into carbon nanofibers. Carbon nanofibers are a valuable, pure carbon-based substance with strength greater than steel, and useful properties for building, for nanoelectronics, industrial catalysis, and for higher capacity lithium-ion batteries. Until now, the carbon nanofibers have been too costly for most applications. Here they're grown efficiently and at very low cost using solar energy. They're grown in an electrochemical reactor, and the electrochemical reactor is illustrated in our animation, if we could start that. In the animation here, we show electrodes immersed in molten lithium carbonate. Electricity is applied, simple electricity, between the two electrodes. At the lower electrode, the cathode, the lithium carbonate, common substance, is split into carbon and lithium oxide. This carbonate at the upper electrode simply releases pure oxygen. The lithium oxide that was formed at the lower electrode reacts with the atmospheric carbon dioxide to make more lithium carbonate. And by this means, the lithium carbonate is continuously replenished. The simple overall reaction is that carbon dioxide comes in from the air, and carbon is made at one electrode and oxygen at the other electrode. But this carbon is in a very special form. It's in the form of carbon nanofibers. And the chemistry, the specific chemistry, is very straightforward, very simple to make the carbon nanofibers, and it's delineated in our new publication. It's available free online as an open access article. The reference is given in the animation. Also, if you're interested in the specific chemistry, just shoot me an email. My email address is also on that animation, and we'll send you the full 2-minute animation of that process. Carbon nanofibers are a very valuable product, as opposed to coal, which costs about $40 a ton, or graphite, which costs about is worth about $1,000 a ton. Carbon nanofibers are worth on the order of $25,000 a ton. We think this gives a very large impetus to convert the carbon dioxide directly into carbon nanofibers from the atmosphere, and provides a reasonable path to bring down the carbon dioxide levels in the atmosphere. Today, carbon nanofibers are used in carbon composites, such as in the Boeing Dreamliner, the lightweight replacement for the body of the plane instead of aluminum magnesium alloys. There's a variety of applications for them, and we believe that this process will substantially bring down the price of carbon nanofibers, driving up the need, the demand for them. We believe the carbon nanofiber market is just at the beginning, the same situation as the plastics market was at the beginning of World War II. It's about to take off. There'll be a wonderful variety of applications, from building materials to renewable energy uses to nanoelectronics. And with that, we provide a wonderful buffer to store the carbon dioxide that was in the atmosphere into a stable, compact form.